Now it's recording. I just had to do it on a different device. Okay, so we've got it recording. So there's the paperweight problem, and then I've got a flat mirror problem, and then this is another version of the coin and the paperweight. It may be the same, but at least you've got it there. And so what we're going to do now is we're going to start. We had started talking about that we were getting ready to do. Come on, just do my slideshow. There we go, from current slide. That we were going to start looking at materials and lenses and looking through and how to get the thin lenses started. So I've got a PowerPoint, but unfortunately none of these have the alt text on them, so I can't post them. So we will kind of walk through them today. So this is looking up from, this is underneath the Pearl Harbor Memorial at over in Hawaii, and you're looking up through the water to the memorial, and you get the distorted surfaces. So this is the paperweight problem, just like what we had done, but looking at the images a little bit better. And there's our formula that we were working with on Wednesday, and here's the magnification that we were looking with on Wednesday. And so this is the coin and the paperweight, the scorpion and the paperweight, all of that. When we are using a refractive surface, these are our sign conventions, so that we've got our object location if it's in front or back or behind the surfaces. And remember, when you guys are setting up for the final, you're going to want to make sure you have your sign conventions, because that's going to give you the best for the positives and the negatives and help you through the exam. Remember that the exam is only from EM waves through optics. So you've got, it's going through electromagnetic waves through optics. So we've done our paperweight problem. If I've got a flat reflecting surface, the image is going to always be virtual, and we are going to have to do the ray diagrams to show where it pops up. So you end up looking at those pieces. And then what the big thing is that R approaches infinity, so we can transform the equations to make it a little simpler when I've got a square surface. And we showed the best I could show through the document camera using the square block of glass, and you can actually see that, yes, that image is up from the bottom. And we went through that on Friday. So now we talked about, on Wednesday, now we talked about that we take those big, thick, different pieces of glass, and we're going to try and make them thin lenses. And we started talking about the fact that when I start having that refraction into and out of the lens, we take care of itself. So we're going to define a thin lens as a piece of glass that's ground so that each of the two refracting surfaces is a segment of either a sphere or a plane. And we also talked about if it's going to be a converging lens or a diverging lens, where the fat location is going to be on the lens. And I've got a diagram for you in this presentation. So thin lenses are commonly used to form images by refraction and optical instruments, most common of which are our glasses. You know, that's our common piece that we've got. So here are our thin lens shapes. We've got what they call a bioconvex, where I've got it, and we remember concave is on this side, so convex is where I'm going to have the bow on the outside. This is called a plano-convex. I've got a plane surface, and I've got the convex surface out here, and this is my convex concave. But remember, we talked about on Wednesday that my thickest portion is going to be in the middle. And these are converging lenses. So they're going to take those rays of light and focus them to a point. So my converging lenses are going to take the rays of light and focus them to a point. Diverging lenses are going to spread those rays out. And we actually showed that on Wednesday with the light box. If I have diverging lenses, the thickest points are going to be at the edges instead of in the middle. And I can have bioconcave, so they're going to look like kind of like an I-beam. I can have a convex concave, and then I can have a plano concave. And again, I'm at the thickest at the edges versus being at the middle. And these have negative focal lengths, whereas my converging lenses have positive focal lengths. So we're going to start to build that sign convention for these particular items. So those are my lenses. So if I've got a focal length, the image distance corresponds to an infinite object distance. This is going to give me the same as I have for mirrors. And thin lenses have two focal points corresponding to the left and the right. So a thin lens is one in which the distance between the surface of the lens and the center of the lens is negligible. So that's the distance between the surface of the lens and the center of the lens is negligible. And we can actually represent them as lines when we actually do our ray diagrams on paper. So there's our converging lenses. We're going to get them into a focus. We actually showed converging lenses on Wednesday, very much just like that this picture is showing, that I take a bunch of parallel rays and I'm going to be able to focus that point in and then get a focal point. And that focus right there is what we call our focal length. And look at where they're drawing the diagram from. It's from the center of my lens. So when I draw ray diagrams, I'm going to use that as my reference point and use it as a straight line on my ray diagrams. Now there's my diverging lens. Again, we kind of showed this a little bit with the mirrors, but with my diverging lens, things are going to spread out, but look at my lines with my ray diagrams so that I can have it back here, and that's why my focus is going to be a negative focus for my diverging lenses. So I will get that. So the focal point is the point where the rays appear to have originated rather than where they actual, and that means it's going to be a virtual image. Okay, because if I have that, it's going to be a virtual image for where things are. So my lens equation is going to look very much like my mirror equation, except in my mirror I've got a 2/r. And I'm going to end up with my ray diagrams just like I did with my mirrors. I can figure out where the image is by giving myself a normal to the plane here. And I can take this through the center that bisects my lens out to my image. Then I have my parallel ray that goes there through the focal point to get my image. And we can actually predict using ray diagrams where that image is going to be. And just like your pinhole camera, if I'm outside my focal length, I'm going to get an inverted image. My magnification, this is going to tell me whether it's upright or upside down. Negative means it's going to be upside down. And I've got that same lens equation or that mirror equation that I had before. So I end up with those. So looking at my sign conventions, if I'm on the front where I'm starting with the object, it's going to be positive. If it becomes the virtual side for the image, it's going to be negative. And this is where my incident light is. If I'm doing the back or the real side, it's going to be, P is going to be negative and Q is going to be positive, and this is my refracted light. So a converging lens has a positive focal length, a diverging lens has a negative focal length. And we've got other sign conventions are right here. So if I've got my in front or in back of the mirror, in front or in back of the mirror, and then I've got my two lens radii because I don't have to have them have the exact same radius, depending on my lens that I'm working with. I don't have to have them to have the same radius is what I'm working on. So I have my convergent lenses, the focal length is positive, diverging lenses, the focal length is negative. So if I'm making a lens, this is where we end up with what we call the lens maker's equation. So whatever my thin lens is going to be, I'm going to take into account this radius associated with it. And that's our lens maker's equation, so that when you go to the optometrist and you go to the optical shop, that's what they're actually doing based on how our eyes see, what kind of lens or magnification we're going to have, or what kind of correction that we have to have for our human lenses. Because over time, our human lenses are going to change shape, and some of us are cursed with it earlier rather than later, and we end up having to have some sort of an equation, a lens maker's equation. So I'm going to switch, hopefully nothing breaks, and we're going to actually do a problem with the lens maker's equation. Ah, goody, nothing broke. So we're good, we're good. So we're going to make a contact lens, and it's made with a thin material, thin clear material. And that material has an index of refraction of 1.66. The lens has an outer radius of +2 centimeters and an inner radius of 2.5 centimeters. And we want to find the focal length. So we have our lens maker's equation, which is 1 over the focal length is equal to the index of refraction of my lens material, minus 1, divided by 1 over R1, and that's going to be my front, minus 1 over R2, and that's my back. So it's pretty straightforward in that I take my 1.66 minus 1 over 2, minus 1 over 2.5, and that gives me 0.66, and I get my 0.5 minus my 0.4, and that gives me my 0.66 times 0.1, which gives me 0.066, and then if I flip it over, I get 15.15 centimeters. I know, I just noticed that. See if that's better. That's a little better. Yeah, I just noticed that on our screen it was washed out too. And it's the end of the semester washouts associated with markers. See if I can darken it up. That help? And then the answer ends up being 1.15 centimeters. And I will tell you there's one lens maker equation on the final. Huh? This end? It's on the top. Yeah, it's the index of refraction. Okay, see if I can go back and not break anything. Woohoo! Yeah, we got back. All right, so there's the lens maker's equation, and that's when we're actually constructing lenses. So, just like with mirrors, we can do a ray diagram. Okay, and ray diagrams allow us to do these geometrically as well as mathematically, so that you can actually check your work using the ray diagrams. So ray diagrams, what we're going to do is the first ray is drawn parallel to the principal axis that passes through the lens and through one of the focal points. The second ray is drawn through the center of the lens, and then it continues in a straight line. And the third ray is drawn from the other focal point and emerges from the lens parallel to the axis. So I'll actually draw one here in just a second. You'll see the diagram to look at it. And so it takes 2 rays to actually locate where the image is, and the 3rd ray is a check. So here's our first ray. It's going to go straight to the principal axis. Then it's going to go through the focal point, and then it's going to come out on the other end. This is the one that gives me my bisection across there, and that's my second. And here's my check, goes through the focal point to this axis and then across. When I have something that has the objects come through, I can still do the same drawings, just that now I've got to have where the rays appear to come from and get me my convergence. And that usually happens when my object is inside the focal point of my image. Okay? And if I put a piece of paper, this image is going to show up on the piece of paper, and it would be a real image. This image won't, because the actual rays of light are on the back side. So this is going to be a virtual image. Because of my sign convention, when I look at my magnification, because this is on the back side or the virtual side, that's going to be negative. I'm going to have a negative in my magnification, which is going to tell me it's going to be upright. So a couple of your questions on the final are going to be, the image is going to be upright and virtual, or the image is going to be inverted and real. So you'll have to describe those images. So that's one of the things you want to look at as you're studying for the final, how to describe the images. And note that the change in the image moves through the focal point. So we'll get there. So when an object is in front of the focal point and it's on the correct side of the lens, I'm going to get an image that's real and inverted, and it's going to be on the back side of the mirror. Okay, real and inverted, and it's going to be on the back side of the mirror, the back side of the lens. And then if I go the other way, it's going to be virtual and upright, and it'll be on the front side of the lens. And that's if my object is placed at a point between the focal point and the major axis. So I strongly encourage you to look at the various diagrams as you're studying for the book, to be looking at how these images work. I can do for diverging lenses. Now remember, these were converging lenses. Okay, diverging lenses, I'm going to use the same ray diagrams, but I have to keep into account of where my rays are going. So we have to kind of keep watching where those rays are going, and the image is going to be on the front side of the lens. And they're always going to be virtual on a diverging lens. So we get the point of intersection, you can draw your rays, and you can get the back rays positive, and then we can put things in combination. But I'm going to switch, and we're going to actually see if we can do a couple problems without having things get totally messed up. All right, I got my problems here. See if I can get a nice, because I need a okay. So we're going to start with a converging lens. And it has a focal length of 5 centimeters. We want to locate the images for objects at 10 centimeters and 2.5 centimeters. And we want to determine the characteristics. Okay, if I do it with the equations, Okay, if I do it with the equations, I've got that, and I have the magnification is minus Q over P. I'm going to rearrange to solve for Q here. And if I do that, I end up with 1 over Q, do the common denominator thing. I get P over FP minus F over FP. So I get 1 over Q is equal to P minus F divided by FP, which means that Q is going to be FP, P minus F. So if I start with a 5 centimeter and a 10 centimeter, my Q is going to be, it's 5 centimeter focal length, 10 centimeters away, and I have 10 minus 5. I end up with a Q of 50 divided by 5 gives me 10 centimeters. And then if I do my magnification, I get a minus 10 because it's going to be my Q over P, and I don't have a negative, which gives me minus 1. The image for my 5 centimeter, or my object at 10 centimeters away is going to be the same size, and it's going to be 10 centimeters in the back. But we want to draw it as well as, get that up there so you guys can see it, as well as just doing it via the calculation. So let's kind of draw it and see if we can get that going here. So what I'm going to do is I'm going to draw a straight line. That's going to be my axis on my page. I'm going to represent my mirror, or my lens. We've been talking mirrors and now we're talking lenses. Just like that. So I've represented my lens. I'm going to put my focal point, I'm going to use my little chart here. I'm going to put my focal point on my chart. So there's my focal point. And I have it on both sides of the lens. And I've actually got a measuring device that's kind of holding me up here. And my object, in this case, is right there at 10 centimeters. And if I'm using a ruler, I've got a nice ruler to be able to have that work out. So, I'm going to take my line. I'm going to draw a line, my first ray, from the top of the object to my lens. I'm going to draw a line through where that intersects and my focus. So I've got that line there. So there's my first ray. My second ray, I'm going to use the line from the top of my object through the center, and I end up there. And my image is going to be where that intersects. And if I am nice and precise, I can do a measurement and show that those are actually the same size. So it's inverted, and it's inverted, and it's going to be the same size, just exactly like our calculation. Now here's my third one for the check. That one I take the focus, and I go through the focus in the top, and then I draw this one parallel. And voila, I've got a nice check for my images. So it's really nice to be able to have that lovely check, to be able to do it graphically. So we're going to do the other one, the one that's at 2.5. You're going to go through the same type of calculation, except now I have a nice handy dandy equation that I don't have to sit there and redo it. So my Q is going to be my FP, P minus F. F is still 5 centimeters. This time it's 2.5. And my P is going to be 2.5 minus 5. If I do that, I get a minus 5. My magnification then becomes my minus Q, which is minus 5, divided by my 5, or no, my minus Q, P is 2.5. 2.5, and that gives me a plus 2. So the plus means it's going to be upright and it's going to be twice the size. Okay, upright and twice the size. So we're going to do the same thing that we just did. Give myself a straight line. Actually, I'm going to do it on the paper this way because we're going to make it big. So I get my straight line. That's my axis. I'm going to put my lens in here. So there's my lens. Now I got to draw my focal lengths. There we go. I've given myself some reference points here. And I'm going to draw just a teeny tiny object because we're going to have it become bigger. If you want to keep your reference points, there's my focal point. This is my focal point. So I'm going to follow the same procedure as I did before. So I've got my line that goes there, except now I've got to have the intersection through this focal point. My focal point's way over there. So there's my line, so it's going here and it's coming back that direction. Okay, so they're coming back that direction. I'm now going to put this one through the center. There we go. And because I wasn't using a nice precise ruler, it didn't come out just appropriately, but it should be more like this. There's my object, or my image, and it's going to be twice the size of my object. And then you can do your lovely handy dandy check. And my check would have us go through this focal point. Let's see. It's harder to do your checks when they're like this. Because I've got to go through the tip, through the focal point. Oh. There it is. And then that bounces back. So this goes up and then it bounces back to give me my image. So that's your third check. So now we'll do a diverging lens. Diverging lens. The lens equations are going to be the same. So this is a diverging lens. Focal point is going to be 30 centimeters. The sign convention now is that that's going to be negative. And we're going to do P at 40 centimeters and at 10 centimeters. So I can just do my Q is equal to F, P minus F, because we've already derived that. And I get my minus 30 times my 40, and I do my 40 minus a minus 30, and that gives me a minus 17.1 centimeters. My Q is going to end up being FP for the other one, P minus F. I get my minus 30 times my 10, and now I get my 10 minus a minus 30, and this one equals a minus 7.5 centimeters. This negative and that negative means that it's going to be in front, which you would expect for a diverging mirror or diverging lens. And when I put it in the magnification, it's going to give me a positive, so we know it's going to be upright. So now I'm just going to do the lens diagram. So I've got my line, I have my lens, and we said this was a 30, so let me give myself a 30. We're going to be smallish this time. So this is going to be my focal point. That's going to be my focal point. The first one is going to be, our first object is going to be at 40. Okay, so there's our 40. And then the second one, we have it at 10. So I have it. So I'm going to draw them both on the same diagram. And I'm going to try and keep this, give ourselves a little bit to play with so that we've got it. And now we can do the drawing. So my first one, draw it parallel to the lens. Then I'm going to go through the focus and where it intersects. And because it's a diverging lens and we know it's going to end up in front, I'm going to need my line that way. So there's one of them. The next one goes through, make sure I got it. Oh, and I also want this one. There we go. And so the first image is going to show up did I got that right? My 40 goes across. I also should have one through here. That one. And then I've got to go. This is going to end up there. There we go. I'm going to redraw it because I've messed it all up. here's going to be my object. This is my focal length there. There's my focal length there. It's a diverging lens. So when I come through here, I go through the focus on the front side. So there's one. Then I go through there, there's two. And there is my image. So that's on the diverging lens side. Now if I do the other one, which was at 10 centimeters, so we'll do that one. Make sure I got it in kind of a right spot. So if I do the one at 10 centimeters, I'm going to do the same thing there. That comes in, gives me along that line. Except now I got to do this line. And this one's image comes up right here. So this was the object 1, this is image 1, this is object 2, this is image 2. But you can always do it with the equations. You can always do it with the equations. Now, like a telescope and a microscope or something along those lines, we do multiple images, or we use multiple lenses. So think about your microscope in biology class. You have your eyepiece lens, right? You have your lens down at the bottom. There's maybe another lens in the middle, and I've got a combination of lenses. And a telescope's going to do the same thing. We're going to use a combination of lenses. So how you work those problems are that the first lens is going to give you an image, and the image becomes the object for the second lens. So the first lens gives you an image, that image becomes the object for the second lens, and then you work the piece. So images formed by, if an image forms by the lens on the back of side of the second lens, then you're going to get it as a virtual object, and then your P becomes negative. So keeping track of those positives and negatives becomes real important when you're dealing with combination lenses. And that's why the lens diagrams work really well for you, because you keep track of where your image is and then where your object is going to be for the next lens. So what happens is this. So I've got a first lens, okay? I've got a first lens, and we can draw from our object, and that's going to give me this image. This image then becomes the object for the second lens, and you can go through the ray diagram and get your second lens, and then you'll ultimately get where the image appears. So when you use combinations of lenses, you're going to be able to use the objects and images back and forth. Lenses have aberrations just like mirrors, and we can have a spherical aberration where things aren't going to line right up, and then I can have a color aberration where I get my red and my blues will separate out. So I can have those color aberrations just like I can have thin lens aberrations, and that gets us through where we are today. We'll do a couple more, talk about double slits and refraction, or double slits and more wave mechanics of light starting next week. but now you've got everything that you're probably going to cover, that I think I've got covered in the final. We will talk about polarization. I'll show you some stuff on the human eye next week. And we guys, we're just about there. Just about there.